All right, we're back. I've taken the liberty to copy some of these results we got from the last slide just to save a little time. As you remember, we have a continuous time signal. It has some generic kind of a spectrum with bandwidth B. That's the highest frequency. So there's the spectrum. Now we're sampling it. Remember, we multiply it by the sample function and we get this thing. And we get this periodic spectrum. So this is xs. X sub s of t indicates we're still in continuous time, but we've just done the sampling operation. We haven't gone to discrete time yet. So this spectrum is also in terms of frequency f. And then we can of course write this was the result we got in terms of an equation. It's just a whole bunch of these x sub c of f's strung out at multiples of the sample frequency. So there's the case for k equals 0, we just get x of f. K equals 1, where we get x of f shifted to the right by 1. This moves down there, etc. Now, let's just chat about this a second. Think about what's happening to this nice, smooth signal. After the sampling process, we get this totally distorted, ruined view of the original signal. Look at what happens. We get the amplitude of the signal, like right there, and then it drops down to 0 and stays 0, so we essentially lose, well, possibly lose the information between samples, and then it shoots back up to here to 0, and it shoots back down, or back up to the amplitude, and shoots back down to 0, shoots up to the amplitude of the signal, back down to 0. This is a terrible signal. We have totally sliced and diced this thing through the sampling process. And the effect in the frequency domain is we still have the original signal, but we now have this high frequency noise, and since they're replicas of the original, we can call them images if we like. They're just images, but they're up at high frequency. They're not supposed to be there. This signal doesn't have them. This does, and these things are what are necessary to reconstruct this terrible kind of shape. And they go on forever. We need an infinite number of them to account for this terrible distortion that we're doing. Well, one other thing I wrote down here is it'll be useful for us to rewrite this in terms of radians per second instead of hertz. So if we want to write KFS in terms of radians per second, remember that Fs is 1 over t, so K omega s, if you like, if that's what we want to put there, is going to be K2 pi over t. So now just sort of rewriting it, and we're not being totally rigorous, but I think you see that you get the gist of this, that and that are kind of the same animal. All right, well, our sampling model has really captured what happens to the signal, to the time domain signal, continuous time. It goes from this to this, and we're still in continuous time, and the original spectrum now has all these images. Well, we still haven't gone to discrete time yet, and as I mentioned earlier, the jump to discrete time, we've kind of the only thing we're going to do with that is take care of the frequency scaling that goes on. Okay, because that's the hard part of this was modeling the periodic spectrum, and now when we make the next jump, change back to my black pen, we're going to go from x of t to x of n. Okay, and remember the way we do that is just to replace the time variable t with n times the sample interval. And I should put sub c on there to remind us that this is the continuous time signal. Remember that we talked about this a bunch of times. The way to relate radian frequency in discrete time to radians per second in continuous time is with t. They're just related by a simple multiple. And this is going to be the frequency scaling problem that I'm going to talk about. And this means that if I just solve for omega, we get a big omega is little omega over t. All right. Well, let's just plug this thing. Let's just plug this. Actually, we're going to plug this thing, and we're going to plug it into there. Okay, just and what you see is we get this. We get, and I'm just going to go ahead and write this as x e to the j omega, which is what you're very used to seeing. That's the discrete time Fourier transform, and I'll justify that in a second. 1 over t times the sum over all k x sub c times omega over t, right? That's just this replaced with that, minus k 2 pi over t, and then I can write that as 1 over t sum x sub c 1 over t. I'm going to factor out the t thing there, omega minus k 2 pi. All right, this is something that we're very used to seeing. This is omega minus k2 pi. This is exactly what we've seen earlier in the semester. This just means this is periodic. It repeats every 2 pi. Okay, so it's periodic. This is explicitly showing the frequency scaling problem that I was talking about. All right, so what we've done is this sort of bridges the gap. There's the discrete time spectrum and there's the continuous time spectrum. So this is what we were after all along. We now see the relationship between the original spectrum x sub c and the discrete time spectrum, and it has built into it the amplitude scaling and the frequency scaling. All right, so let me jot down a little example to kind of illustrate the same examples we've been doing. So in continuous time we have this signal, right, as a function of t, and it has spectrum that looks like that. Bandwidth b. And one other thing I'm going to do is just to remind us that, remember that how we looked at the symmetry of these spectra, discrete time Fourier transforms, and the left side is exactly the same as the right side, except they're complex conjugates of each other. All right, so keep that in mind. When we go to discrete time, we can draw a straight line, discrete time. Now we get this original signal, but now we're drawing them as a stem plot. Each one of these lines represents a single element in a vector that we call x of n. Time variable is now n instead of t, and whereas this is the continuous time Fourier transform of the continuous time signal, the continuous time Fourier transform of the discrete time, or the say that again, the discrete time Fourier transform is going to look like this. Okay, it's going to look like a whole bunch of these triangles going out forever. A omega, little omega, is the frequency variable. And it's going to look like that. We still have, I mean, these are just replicas of this, but they're scaled by amplitude and frequency. We still have the complex conjugate property, so the left side, these are all just copies of each other, but just moved out to a different frequency. So this is at 0, 2 pi, 4 pi, 6 pi. Okay, the amplitude is A over T. This is in hertz and this is in radians, so I kind of mix my units a little bit. But whereas this has a bandwidth of B hertz, this has a bandwidth in terms of radians. Let me call it beta, where beta is equal to 2 pi B over Fs. Okay, for example, what if Fs is 1,000 or 10,000? Then beta is equal to 2 pi B over 10,000. For example, if B is say 1,000, then beta is equal to 2 pi times 1,000 over 10,000, which is pi over 5 radians per sample. So here's the frequency scaling that's happened. We've gone from 1,000 hertz as a bandwidth here. All of that's now squished in to so we've gone from 0 to 1,000 hertz. Now we've squished it to omega between 0 and pi over 5. So all of this, that's a big number, 1,000, is now squished into pi over 5. So that's the frequency scaling aspect of this. Okay, so next we're going to talk about some notation and some more practical aspects of this. I'll be back